First of all, thank you for organizers for giving me an opportunity to come here and also present this work here. So before going to
Yes, this laptop is extraordinarily sensitive.
I see.
Yeah,
I see.
here, and you can try. You know,
Yeah.
We can also move the table. It is recording.
Now I got it why people are doing here. Anyway, yeah, thank you for this opportunity. And I like to talk about transition dynamics of some ground state in QCD, some topological nature. And in particular, we find some slowing down motion of the topological object, generally called soliton, on that near that transition. Okay, so yeah, this work is in collaboration with Kentaro Nishimura. He's also a postdoc at KU. Okay, let's start from some famous story. So Landau says phase transition can classify whether discontinuity or continuity. So discontinuous one is first order and the other is second order. On top of that, Jan says the second order phase transition has further breakdown regarding of the topology of the system. So most standard one is called the so-called instability type. This is his name. He named it about it like a standard trivial second order phase transition, like which is described by local order parameters such as the ferromagnetism of ferromagnet. In addition, there is another type of continuous transition which is characterized by some topological nature, and he named it kind of class of the second order phase transition as nuclear type transition, as shown in this article. And today in my talk, I'd like to focusing on this topological nuclear type transition. So what is nuclear type transition? So this is this transition is characterized by an order parameter with some topological constraint, and there's some various examples on this transition. For example, like type 2 superconductors, as I will explain soon, and also chiral magnets, and also porosity liquid crystal. And here I show some example on the type 2 superconductors. So type 2 superconductor is not usual superconductor, so there's permission of some insertion of the flux at the intermediate state of this superconductive Meissner state and the normal conductivity. And if one increase the external magnetic field, the system permits some insertion of flux, quantized flux, then finally one gets the normal state. And here is the plot of the magnetism. And what I want to discuss here is the transition between this Meissner effect and mixed state shown as this near this transition magnetic field H1, and as a schematic picture shown here. And this kind of transition, there's some universal behavior described by this logarithmic behavior, which comes from some asymptotic form of the special solution of the solitons in these systems. So this is kind of universal logarithmic critical behavior around this nuclear type transition. And today I'd like to focusing on this kind of transition in QCD. Then next question is how about the dynamics? So as for the instability type, as a usual standard second order phase transition, which as I mentioned before, there is a universal feature called the critical slowing down. Critical slowing down is the slowing down of the hydraulic modes, which coupled with the order parameters such as relaxation modes or diffusion modes or maybe velocity of the non-Ghost mode. And as for example, near the liquid gas critical point, the diffusion constant vanishes. So what does this mean is, so if you put some, this is a schematic picture, but if you put some red ink into the water, this ink will spread, and this phenomenon is the diffusion. But near the QCD critical point, these diffusions are very slow, and at the limit of the limit of this liquid gas critical point, it takes infinite time to get some equilibrium or ground state. So this is a slowing down of some kind of dissipative phenomenon in the usual instability type transition. And today what I'm going to discuss about is what about the nuclear dynamics near the nucleation type transition. And there's an interesting thing which cannot be found in the usual standard stability type second order phase distribution is the motion of the topological objects, such as the domain walls or vertices, which called the solitons in general. Okay, then actually we will discuss some dynamics of the one of the solitons in QCD. Okay, so but as long as I know, as long as I know, there is no such kind of general studies of this dynamics of this nuclear transition, and we would like to give up the first example in the QCD. Okay, so our purpose has been based on also the context of QCD. So here is the so-called QCD phase diagram. So the motivation here is to understand the state of matter at extreme condition described by the QCD scale. So here, x-axis denotes the baryon chemical potential, which corresponds to the density of the system, how dense the system is, and the range is like a QCD scale of density. And also the y-axis denotes the temperature. This is just temperature, so it just gives some high hot temperature compared to this our ordinary life. So there, among others, there are several phases called hadron phase, which the quarks and gluons are confined like this life. And also I will not discuss, but there is like a co-gluon plasma phases where the gluons are deconfined, and also the quarks can form a color superconductivity at high density. But among others, today I would like to focusing on is the strong magnetic field, like in this direction, third direction, and there's some. I think there's many points of interesting thing, but one of them is relation to the anomaly, as I will explain later. So there will be a non-trivial ground state called by anomaly, and what we will discuss was this so-called chiral soliton that is in QCD at high baryon, at finite baryon density and the finite magnetic field. So it has been known from Damson, Stefanov, and also Thomas Browner and Naoki Yamamoto. There is a phase transition from the QCD vacuum or nuclear matter to this kind of chiral soliton lattice. So let me briefly explain about the chiral soliton lattice. So this is, as I mentioned, this is the anomaly-related ground state of QCD at finite baryon chemical potential and finite magnetic field. And what the chiral soliton lattice can be understood by three terminology, which forms chiral soliton lattice for each. The first, chiral means violating parity. So this is actually the condensation or configuration of the Nambu-Goldstone mode of QCD, what is called pions. But this is general Nambu-Goldstone mode. Then this Nambu-Goldstone mode has some configuration which breaks parity first. And the second is the carrying soliton, means carrying topological charge. So pion forms a ground state which have some topological nature, and this is a soliton. And as the last, lattice is just it. So lattice breaks transition symmetry, and here the pions form a lattice periodic configuration as the usual lattice. So here is the example of this configuration of pion. So this x-axis denotes the space in unit of the pion mass, and this y-axis is the value of the phase value or pions. So you can see this blue line is the actual configuration. So you can see like a step structure of pions, and this will be shown as the ground state of QCD due to some anomalous effect. And here dot line denotes the derivative. So it's just a derivative. So when it grows, when the blue lines are growing, and this behaves like a solid, rigid object, like a motion itself. So it will be called. It is generally called solid. And the characteristic period of this lattice pitch is a function of magnetic field. And yeah, I will go back to this point later. So this is what it is chiral soliton lattice as the ground state. Then what we want to describe is the hydrodynamic evolution to this ground state. And here, what we found is some novel transition dynamics near this nucleotide transition. So here, I showed some spatial configuration of derivative. The ground state is nothing but this dotted line, and I will explain later, but we just describe a dynamics from two types of initial condition. One is the initial boundary condition, which have some solitonic structure at the different point of the ground state, and the other is to prepare some initial configuration which doesn't have a solitonic structure. Then we just we will calculate the dynamical evolution, as I will explain later. Then we just calculate the time evolution of this configuration, and we calculate the characteristic time to reach to this ground state for each configuration. Then what is interesting here is plotted in this right figure. So we just choose the magnetic field because we are interested in some transition dynamic. Yeah, the dynamics near the phase transition. So, and there's qualitatively different behavior from these two initial configurations. So one with the solitonic strips, one with the solitonic structure initial configuration, going to slow down as magnetic field increase. But the local relaxation, which coming from this green initial configuration, doesn't have the same magnetic field dependence. So this kind of motion of the topological slowing down, so as topological soliton slows down, but the local relaxation kept finite, might be a novel transition dynamics of this solitonic ground state. So today I'd like to discuss about this. Okay, so here is the end of the introduction. Yes, please.
So you said that there are some these lattice.
Yeah.
So that lattice means that there are some spontaneous Lorentz symmetry breaking in this system. That's usually what happens. Is there?
Lorentz symmetry will be also, yeah.
Or that is the huge. I don't know. Is it?
Magnetic field already breaks it, right? So magnetic field, you turn on the background magnetic field, you break Lorentz invariant.
Even
Not as much, yes.
Yeah, but not much, right? So, but you still have the. Like, I just asking this lattice.
Breaks Lorentz symmetry or not?
Is automatically is spontaneously?
Not spontaneous, I think.
Oh, it's given by say.
Yeah.
Okay.
Yeah. Actually, in order to get this configuration, we need some dissipation effect. So that also breaks some Lorentz symmetry.
I get zero chemical potential.
Could
I get zero chemical potential.
I use it what?
At zero chemical potential.
But
Chemical potential.
yeah, this is finite variable chemical potential result.
Okay, so do you also have skyrmions in your picture?
Skyrmion. Kind of skyrmion. But yeah, kind of, but not the direct skyrmion. Yeah, this was great. Yeah. Okay. Okay, so here's the outline. So I will explain our setup. Then as a second stage, I will explain the formulation, time evolution equation at low energy and low long scale. Then I will briefly review about the chiral soliton lattice itself. And the fourth stage, I will show some numerical results that I explained before. Okay. So here is the setup. So we will describe the system with the two flavor QCD at finite temperature, biochemical potential, and magnetic field, such that the chiral soliton lattice exists as a ground state. And in that point of view, we need to consider, or maybe real is a finite mass, so we do that. Then we want to formulate some hydrodynamics or low energy, low momentum effective theory of the system, and include some dissipation to describe the dissipative evolution of the system. So the basic ingredients or low energy degrees of freedom in order to construct a theory is called the hydrogen variables, and in our case, we use two variables. One is the neutral pion, which is related to phase degrees of freedom of this called bilinear, and this pi is the degrees of normalized degrees of freedom of the pion. And here T3 is the generator of SU2 SU2 generator.
That's a quick question
Yes.
about terminology. Why do you call it hydrodynamic?
Uh-huh.
Is it actual liquid of pions or it's not? I mean, there should be some local equilibrations of pions on short scales to have hydrodynamics. Is
Yeah.
this the regime that you're considering?
What I want to say is not so. might be a subtle point, but I want to care about some. We will discuss finite pion math. So at the Lorentz limit, it will be how to say short range degrees of freedom, but we just want to formulate the maybe length scale such that not so much how to say low energy, such that the pion mass finite pion mass is cared. Is that what maybe?
Not sure. So
Okay.
basically, I'm trying to understand, is this low energy effective theory,
Yeah,
or
yeah.
is this really hydrodynamics?
What do you mean by really?
Hydrodynamics means that you have actual equilibration of the local degrees of freedom, and you have locally like equilibrated matter, but at large scales,
Yeah,
you
yeah,
may
yeah.
have some
Yeah.
hydrodynamic behavior.
Yeah. I think we are in the same.
Okay.
Yeah. Maybe we also neglect energy and momentum. That is also usually included in hydrodynamics. But this is a low energy in the sense of low energy effective theory. This is hydrodynamics. Yeah. Okay. So yeah, we will describe the dynamics of this neutral pion and also the quantum charge associated with the same chiral symmetry. Will be also important to describe the dynamics. And yeah, let me say about so neutral pion is the ghost mode associated with the chiral symmetry. Yeah. Yeah, for the audience who will not familiar with this. Okay, so let's go to the formulation. First, we prepared the Hamiltonian to describe the dynamics for the next slide. So here is the most general Hamiltonian density, which consists with the symmetry of the microscopic QCD at finite biochemical potential and magnetic field. And it consists of the three parts. One is much more standard. So this is the like a theory of a pion itself. So this gives by the gradient of the pion, like kinetic term, and this phi is the pion decay constant. And this corresponds to like a rigidity of the order. So in case of the superfluidity, this is called like a stiffness constant in terminology of the same non-ghost mode. But this is the QCD. So non-ghost mode is the symmetry breaking of approximate chiral symmetry. So this is just one of the non-ghost modes. Yeah, let me so here and the chiral symmetry is not the exact symmetry due to the finite group mass, but it is the approximate symmetry. So from the symmetry constraint, this mass term is also determined, and this m pi is the pion mass. So this is the first term, and you can derive this from the chiral and the so-called side chiral calculation. And the second one is the density part, which introduced as the Gaussian term, and this chi corresponds to the actual isospin susceptibility. So this is the response of the actual isospin density from the fluctuation of the corresponding chemical potential. So this is susceptibility, and this is density term. And the last one term is, I could not explain about the details, but this is something anomaly related term or topological term of the finite biochemical potential and magnetic field. And please note here that there is a derivative of the pion configuration. So these terms favors the inhomogeneity, which has a different behavior of this kinetic term. So there will be a competition of this kinetic term and its anomalous term, which favor the inhomogeneous configuration. And finally, at strong magnetic field, such term overcomes the kinetic term, then the finite inhomogeneous configurations exist in the graph.
Why would you trust this effective action at large P? This effective action is valid at low
B, yeah.
low external fields.
Yes.
Small
Within,
temperature.
yes, actually, thank you. So these are within the applicability of the chiral effective field. So if we will not consider about so strong magnetic field. Yes, think about it.
But I think the question is whether you can trust it at the point where you make the soliton lattice.
Whether we can trust or not.
Yeah, because you need to beat something with F5 in it. So yeah, by the time B and BB are big enough to compete with F5 in the kinetic term, can you still trust this? Are higher derivative terms important?
I think we can trust this. Yeah.
It could be is proportional to n pi.
Yeah, BCS, yeah.
Okay.
Yeah,
I am
we can check whether it is within the applicability or not. Yeah, from the strength of the magnetic field, as I will explain it. Yeah.
I think this is likely to be a very stupid question, but what is rho in terms of phi?
Oh, thank you about that. Rho is the actual isospin charge, density. So this is
It has an expression in terms of phi, right? Or no?
no.
Then why is it part of the effective theory?
Oh, thank you for your comment. So, we want to include all of the low energy degrees of freedom of the system. So that can be number Gauss numbers, for example, and also charge density. Charge quantity related to conduct charge is also low energy degrees of freedom. So we need to include that to describe the dynamics. And in particular, for the dynamics, it will be phrased as important.
It's not phi down. I thought the rho is phi
I
down.
was hoping for some answer like that, yeah.
But yeah, so it will be related, or it will be related by equation motion itself. Yeah. Yeah.
Equal to phi down. Right?
Yeah, it's something, with some additional thing. I will explain it. Thank you for
But the various currents are just built out of the Olson bosons. That's what I thought. So at low energies, which is the only place you can trust us anyway. So that's why I thought it should have an expression.
But low energy here is 1G.
Well, but you're using pi, so it better be pi, right? So anyway, it's okay.
Did you
It's
know
okay.
the expression for rho in the previous slide?
Yeah, I had,
But it wasn't in terms of
What was
pi.
it? Was it?
It was in terms of microscopic degrees of freedom, and I was asking for pi.
It really is in the color space.
3 is in flavor space.
I think it's what the song said.
It's the S, it's part of the S2, it's the cartan of the S2 to the
Yeah.
Okay,
That's why I think it's pi.
Yeah.
I know.
Yeah, pi naught, yeah.
Okay.
so it's fine.
Any other question? Okay, so let me go to the next. Okay, so here is the Hamiltonian. So we here is the dynamics. How to the formulate dynamical formation. So we just formulate the low energy effective theory with dissipation, and the general description is given by, for example, this Chaikin and Lubensky textbook, and also Son's paper, and also. So here I show the time evolution equation for the neutral pion first, or maybe I will not explicitly write down the density part because of the time constriction, but it has a general same structure. So it consists of two parts. One is called reversible term and the dissipative term, which keeps the time reversal symmetry or breaks time reversal symmetry for each. So the reversible term consists of some is determined kinematically or symmetry constraint. And this is included by this Poisson bracket, which also related to the symmetry of the system. And also this Hamiltonian is the one I introduced. So it's also proportional to the variation of this Hamiltonian. And this Poisson bracket mean we portray this Poisson bracket as number Gauss mode and the charge densities are canonical conjugate, which can be also shown by the symmetry of the system. And we use the Poisson bracket, and also as for the time dissipative term, we expand the coefficient of this variation of the Hamiltonian with respect to the derivative. And there's constraint from the conservation law in general, but these pion degrees of freedom are no longer related to the conservation law itself. So the leading term derivative expansion will be the constant, and this will be a kinetic coefficient of the pions, and in this case it is called the relaxation rate of the pion. So this is the pion part, and we just calculate this variation and put this Poisson bracket, and we write down the evolution equation. And here is our equation of motions. So the first one is I explained the explicit expression of the previous page, and the second one is the what we obtained from doing the same things for the charge density. But there is a constraint from the conservation law because that is a charge density. So the derivative expansion of this dissipative term starts from the number square. And the coefficient corresponds to the conductivity of this actual isospin charge. And I'd like to emphasize here, this is a nonlinear and dissipative generalization of previous works, including Son and 2000 and Son and Stefan's 2020 2002, and both are essential for having the relaxation process of this Chiral-soliton lattice, because Chiral-soliton lattice is a finite Cope mass effect and also a nonlinear effect, and also dissipation is needed to have the ground state. Otherwise, the system will keep evolving. So dissipative is very important for our purpose.
But can you explain? I don't understand how do you derive dissipation?
Dissipation is that
If you're in the realm of effective field theory, you don't have dissipation. If you're in the realm of finite temperature and you integrate out over many states that you don't know the details of, you have dissipation. Where do you have dissipation? If you just decided that you're in the low energy chiral Lagrangian, no, there is no dissipation.
Oh, I see. So, okay, let me see. So, we are trying to do some hydrodynamics and increase dissipation. So,
So it's like you're doing normal fluid and superfluid coupled to each other.
yeah, something like that. Yes, yes, I think so.
So it's not effective field theory anymore.
Let's see.
Maybe rephrasing the question, what's the mechanism for that dissipation?
If you're at low energy, there is no dissipation. I mean, if you're in the chiral Lagrangian.
How about
Dissipation
finite
from there.
temperature or something? We are thinking about finite temperature at least because dissipation is.
There's kind of symmetry and temperature.
So is this like ion scattering? I mean,
Yeah,
what's the mechanism behind?
Yeah. Maybe I know several works calculating kinetic coefficients of by using the chiral perturbation theory, but maybe in Keltis formalism. So that will give the exact form of these parameters at this stage, I think. So one can, in principle, calculate by using some microscopic theory. But here I would like to, say something universal. I mean, using hydrodynamics in the theory which have the same symmetry will have the same hydrodynamic equations, but the coefficients might be depends on the system. But I want to try here is how to say in the position of some general point of view. Okay, and we will working on this 1+1D for the numerical calculation, and we choose the spatial direction in parallel to the external magnetic field. So here is the evolution equation that we will need for our purpose, and our result is this numerical calculation. Okay, so let's go to the Chiral-soliton lattice. So here we find the stationary solution of our equation, dynamical equation, and that has a solution related with the solution nothing but the Chiral-soliton lattice. So here is this pi bar means the stationary solution with independence of time, and this is the equation of that I written down before, but this time independent configuration. And this includes the configuration of the Chiral-soliton lattice known, and here is updated in terms of the dissipation spell, proportional to the kinetic coefficient and also the pi of mass. So here in this figure, I just brought the unit of the Chiral-soliton lattice configuration, and you can see here some slightly modification due to this dissipation term. So it becomes just a steeper, steeper thing. So this is the numerical solution of this equation. And I'd like to go into a little more details about the property of QCD, Chiral-soliton lattice, for example, relation to the magnetic field. So for that purpose, let us now forget about this dissipation and use some analytic solution. That is a merit of that regime. So here at the big bit, so there's no dissipation. This equation, the first term and this left-hand side is mathematically equivalent to the pendulum dynamic evolution shown here, but the analogy is standing for this t time coordinate in the pendulum is now d spatial. So we know the solution of the pendulum is written by the maybe difficult Jacobi elliptic function, but the details are not important. So here the existence of the analytic solution is shown in this beta equal to 0 limit, and it is written down in this form. So here, Sn is some Jacobi elliptic function, and also it depends on some elliptic modulus called K, which correspond to the initial point of this pendulum case. Initial point, yeah. Then at this point, this K is a parameter, but I will at the next stage I will connect to the magnetic field. And as we also know from this pendulum, this solution has a periodic periodicity, and this periodic length also determined by this one of the complete elliptic function. So for the first kind. So anyway, these functions might be complicated, but it is analytically given. Okay. Then next, let us connect to the related to the magnetic field. So at this stage, as I explained, this K is a parameter, but now we determine this K from the energy minimization condition, which includes the anomaly term. So here we just substitute the configuration of the previous solution to the Hamiltonian, include with some parameter K, and we minimize the energy with respect to K. And this manipulation is shown to be correspond to this equation, also using one of the complete elliptic function of the second kind, and we determine this K function as a function B, and I explain how to do this. So here, blue plot is the left-hand side as a function of K, and the right-hand side is the external magnetic field, which we can tune. Then we tune this yellow colors correspond to the value of B. Then we determine the parameter K as a function of B. Then finally, we put this K as a function of B, for example, in the periodic length. Then we can calculate a picture of this chiral soliton lattice as a function of magnetic field. And this is shown as here. So you can see here, if the magnetic field is closer to this critical magnetic field, normalized here, this period becomes larger and larger. And if we could include, if we B equals to BCS is very long period, and if we increase the magnetic field, this period is becoming shorter and shorter. As this shows, this figure shows. And I will come back to this point later. So anyway, this is the magnetic field dependence of the period of this chiral soliton lattice. Okay. Do you have any questions so far?
Mu is,
Sorry.
mu is baryon chemical potential.
Yes, mu is baryon chemical potential. And also, I'm sorry about that. So BCSL is critical magnetic field. Expression of the critical magnetic field is now obtained in terms of the parameters in the from some condition of this construction. Okay. Then let's also discuss about some topological charges. So this is Hamiltonian that I explained before. Then one can calculate the baryon number as the derivative of the baryon chemical potential, and one can calculate the baryon number for each unit, integrating by 0 to the one period. And if you calculate this derivative, you can find this is the integrand is proportional to the gradient of phi. So this is total derivative. So this integral is only determining the value of the pitch h. Then this will give some topological quantity as per unit lattice. So baryon number B over magnetic field over 2 pi is quantized for per unit chiral soliton lattice. So
The units, it seems like per unit area.
Per unit lattice. Per unit.
No, per unit transverse area.
Yeah, thank you, exactly, yes. So I also say about the direction to this magnetic field, but there is a transverse plane. So yeah, Igor, point out that. Thank you.
And that's why I shouldn't be surprised to see NB, which is normally an integer, being equal to something, but it's not obviously an integer. I mean, B is whatever you want.
Oh yeah. So yeah, that's right.
So it's because it's very number per area or something.
Yeah. Thank you. Yeah. Continuous in terms of B. Yeah.
EV and that integrated to the magnetic flux,
Yeah,
which is quantized.
okay.
Thank you.
Okay, that makes sense.
So, and also we have the same things for the magnetism, and magnetization is defined by the derivative of this B, and you will have the same calculation. So in this case, one soliton has quantized baryon number or magnetization for each. Yeah, so these are the topological quantity in this ground state. Okay, then now we can discuss now the logarithmic behavior as I explained in the introduction on this QCD case. So what we want to use is the symplectic form of the elliptic functions, and valid at this near the phase transition point, and you can see that the periodic length is some kind of logarithmic behavior, and the baryon number, and due to this fact, the baryon number of the fixed length system would have this kind of logarithmic behavior as shown in this. So this is kind of a critical logarithmic behavior of this chiral soliton lattice. By the way, where was when
3:30 until 3:30.
The log comes from the explicit solution and this now.
yes. Thank you. Yes. Okay, so let us discuss about the dynamics now. So here, I will explain about the dynamic setup. So we fix a system size L in the biomass unit like 8, and we change the strength of the magnetic field discontinuously. And what we do here is this: we fix the system size to, for example, like 8, and we tune the magnetic field as near magnetic field, and also this point, which has the half length of the system, the periodic has the half length, and the next stage have the 1/3 of the system size. So we tune the magnetic field in discontinuity way, here and here and here and here and here, and so goes on. And we discuss the magnetic field dependence of this transition dynamics. Dissipated process to each of the kink states. So each state has a different number of kinks because the periods are going shorter and shorter if we include the magnetic field. So this one has a 1 kink, and this stage have a 2 kinks, 3 kinks, blah, blah, blah. I will show the movies later. Anyway, and we use the 2 kinds of initial boundary condition. One is motivated by some quench of the magnetic field. So we switch on magnetic field at some time t0 to realize so each of these ground state eventually. So there will be a transition from vacuum to the kink state from this condition 1. And as for the second case, we prepare an initial configuration, but which doesn't have a kink state as the initial. So this is just a linear configuration of the pilot we use for this second case. And yeah, let's see the movies. So here is the case of the second case. So this is the derivative of the pion. So we prepare the linear configuration of pion. The derivative is fixed as homogeneous. Then this dots will be the ground state. So let's look at it. So here you can see the initial configuration flat becoming this kink structure eventually. And it takes like 20 seconds in this time unit. Okay, then so this is the magnetic field. Magnetic field closer to the critical magnetic field. So let's increase the magnetic field a little. So here the ground state will be 2 kink state due to the short period. Then you can see the similar relaxation process from this initial configuration. Okay. So then let us look about the case 1. In this case, the solitons are inserted like from the edge, and look at this here. There, the solitons are moving to this ground state position, but it takes so long time correspond to the previous page. Look at this time unit. It takes like 800 units compared to the 20 seconds as from the previous one. Moreover, if you look at this kink relatively far away from the critical magnetic field, it only takes like 80 seconds compared to this 800 seconds. So as compared to this, in terms of magnetic field, the motion of the soliton becomes slowing near the critical magnetic field. And this will be some novel solitonic motion as long as we know. So let us quantify this behavior. So we quantify how fast this stationary state appears near the B equals to BCSL, and we define some characteristic rate motivated by this exponential decay by computing the deviation of this pion configuration from the ground state and integrated through the total system, and we obtain the characteristic time tau such that the initial deviation becoming exponentially decayed from the initial deviation. And this is the figure that I shown in the introduction. So you can see different magnetic field behavior for each of the initial configuration. Okay, discussion. So as we showed, as the CSL transition approach, B goes to BCSL from above, we found the slowing down motion of soliton. And we may interpret it like this. So as B goes to BCSL, the number of kinks are decreasing, so there will be a less repulsion from the other solitons. In general, solitons have a repulsion, but near the critical magnetic field, that will be small. So that will be the origin of how this supercritical motion becoming slower. On the other hand, finite local relaxation might be understood by the decay of the gaps excited mode, which can also calculated by the soliton solution, and it will be shown that the B goes to BCSL, this gap should be gap, even as the B goes to BCSL. So this is the reason we interpreted why this local relaxation doesn't slow it down on this case. And this kind of different behavior might be a novel class of the second order transition, where the motion of topological soliton only slows down, but not local relaxation or dissipation in general will not slow down. So this is kind of new dynamics near the transition of the maybe a nuclear type transition, which is different from the ordinal second order phase transition, not related to the part. Okay, so let me summarize my talk. We discussed the low energy dynamics near the CS transition in the QCD, and we found the solution. Soliton motion slows down whereas the local relaxation is finite. And from these findings, we can say that genetic time to the ground state on this case depends on the initial configuration, whether it forms a soliton structure or not. And we are now arguing, or maybe want to understand, in many systems of this kind of nuclear phase transition, maybe including type 2 superconductor or some vortex system or any others, and it might want to know this might be a universal feature of this nucleation type transition or not. Thank you for your attention.
I'm a bit confused about the boundary conditions that you impose to get these solutions. Naively, when I think about this lattice in an infinite space, the location of the peaks will not be linked to anything that will be translational to freedom. And
that is the equal to BCSL enemy.
Yeah, but if you take this finite system essentially and impose properly boundary conditions to mimic infinite system, the location of the peak will not be in the middle, but anywhere. It's fine anywhere.
Yeah.
And your two different modes, they actually might be feeling that in some way through the boundary conditions, because the mode could be basically pinged at any location and it slowly approaches the middle. So the question is, what kind of boundary condition is pushing it to the middle?
Okay.
Is it the artifact of boundary conditions or truly slowing down?
How do you distinguish, like automatically or?
Well, as I say, if you impose some periodic conditions such that the peak could be in any location, then basically it doesn't have to move at all. It would stay there at the edge, and basically it doesn't have to move, it's already in the ground state.
Yeah,
so
but infinite large limits. So if you consider some finite lengths.
Yeah, but that depends on the boundary conditions. Now that's exactly the question. What do you impose as the boundary condition? Why it doesn't stay there?
Why does it bother moving?
Exactly. Why does it even want to move to the middle? What's pushing it into the middle?
Pushing it is the energy is much more low when this soliton is in the middle, because there's if you have this bump near the boundary, it's caused some kinetic energy. So this moves to this moves the soliton to the middle or away from the.
But then it's a boundary effect.
But that's a boundary effect again, because in an infinite system, I could pick one of those cells and basically look at any position with respect to this peak, and it can stay on the side, and it will be just as lowest energy as anywhere else. So when you're imposing the boundary conditions, somehow you have to protect this translational symmetry that the peak can be located anywhere.
You didn't use periodic boundary conditions, right?
I didn't, yeah.
So if it's not too hard, you might want to try and see what happens.
I don't understand.
I'm saying that if the boundary conditions is periodic, then basically it can stay where it was at the very beginning. It doesn't have to move. And therefore, there
if
is
you
no
have-
slowing down.
We cannot have this in the periodic boundary condition because we need to how to say, so at the boundary, the phase should be 0 to 2 pi to have this kind of king structure.
But you want don't you want the translation symmetry to be spontaneously broken, not explicitly broken by your choices as the simulator? It's very awkward if you break the translation symmetry by hand and then continue from there. Wouldn't it be nice if you could preserve it and then see the spontaneous breaking? Isn't that
Maybe
conceptually-
reformulating it, are you sure that this is not the boundary effect? Boundary conditions effect. So if you take exactly the same simulations, but in an infinite system, infinite lattice, would you have the same kind of slowing down?
As long as I understand, at least we need to consider a finite system. Otherwise, if we adjust that, so if we consider an infinite system, then there's no, how to say, for particular point of this bump, so there's no motion. That's correct, I think. And that is the limit, that corresponds to the limit here, I think. So this means this is small, but we take some finite because of this finite system. So but what you mentioned is correspond to this dot, I think. But
somehow,
but we are arguing. So if you fix L and then increase the magnetic field, then this kind of speed of the motion of the soliton becoming slowing and slowing down as a function of V.
I can say different. The solutions are given by Jacobi theta
Yes,
functions.
yes.
And what you are looking at is you start with some initial condition, which is not a Jacobi theta function. And that then relaxes to the Jacobi theta functions. Is that what you are doing?
I think it is not a totally Jacobi function at the initial. Otherwise, it will not be moved.
No, the initial one is not a Jacobi.
Yeah, not exactly. Yeah, not exactly Jacobi.
Yeah, otherwise it doesn't.
Yeah.
Jacobi theta.
Yeah, thank you. So that's that might be the reason it moves, but it looks similar. But it is not, I think. That's right. I think.
other question?
Yes, please.
I'm not sure, I've seen what is the effect of that diffusion.
Diffusion.
You introduced it somewhere in the middle,
Yes.
and then when you were showing the solution, I'm not sure it played any role or not.
No. We don't have any dissipation, then this pump will not stop. Boom. Like,
Where will it go?
no, there's no. So there's if we don't have dissipation, everything does not, how to say, subtle. I mean, so everyone should moving
Okay, so
from the initial energy.
there is phase transition at 0 temperature, or are you talking about phase transition at finite temperature?
What I'm discussing is the finite temperature because
So it's a phase transition at finite temperature you're claiming.
yes.
There is no phase transition at 0 temperature. I thought the phase
There's
transition
supposed
was at 0 temperature.
Oh, and recently it has been shown or discussed about this finite temperature generalization on this parasoliton lattice. So
It has to be, there's a phase transition at 0 temperature?
yeah.
It's connected.
Yeah, but
But it can be second order as well. That sounds the same. Usually it's second order at one point, and then it's first order. Usually it's zero temperature, it's first, so it's second order, and then it can be first order and final temperature or something, but being second order everywhere sounds very atypical.
Okay, yeah, I will check later. Yeah, but I think,
it's all, it's all classical, right? So classically, you might think it's second order, but if you don't calculate quantum corrections, you might miss that it gets first order. This is like in the Higgs model, right? This is the famous falling line breakdown. Classically, it looks like it's second order. You really do the careful one loop analysis, you discover it's weakly first order. So this is all classical. So you have no way of seeing that.
yeah, maybe, yeah, what I want to also say is, yeah, this is different from ordinary canonical phase transition in the sense I mentioned in the introduction. So, yeah.
And also this slowing down, or whatever criticality has nothing to do with quantum, critical fluctuations, it seems.
Yeah, this is, yeah.
It's
So-
again, in a sense, totally classical
Well,
fact somehow.
I mean, I was a bit confused because if it's really, you're dealing with a second order phase transition, then there are, the correlation length diverges there, so I.
Oh, but
really
I
done
want
classical analysis.
So yeah, that's also the maybe different point. So
Yeah.
we are also looking about correlation lengths, but the yeah, this criticality doesn't happen from the large correlation length.
No,
Yes, this is standard instability type. So this is something related to the length long period. This is another scale of the the system.
you're saying there can be second order phase transitions at which the
Con-
correlation length is
Yeah. So
finite.
But so yeah, I want to emphasize here is this is different from usual critical system described by the correlation.
Okay.
Yeah. Yeah, we are also interested how it difficult. They are different. Yes.
I see.
Yeah. Yeah. That's a good point.